What we're going to take a look at today is we're going to be talking about how it is that we utilize matrices in order to understand the unions of digraphs. In particular, we're going to calculate the transitive closure of a digraph utilizing this matrix addition. In order to do that, we want to recall a couple of things from some previous videos and some things that we've learned before. One, that we have a directed graph G, and that can be represented using an adjacency matrix, which we're going to call A. And then secondly, a graph power, which is G to the K, which is essentially G composed with itself several times, can be calculated by multiplying A, the adjacency matrix, by itself K times. And we're going to represent that as A to the K. Let's show how to do matrix addition using Boolean operations. First, two matrices can only be added if they have the same dimensions. That's the same number of rows and the same number of columns. If we add two matrices A and B, we add them component-wise. So space Mn in A gets added to space Mn in B, and then gets placed in the location Mn in A plus B. Recall that for Boolean operations, 0 plus 0 is going to equal 0, 1 plus 0 equals 1, 0 plus 1 equals 1, and 1 plus 1 equals 1. So let's go in and do an example. So we'll add these two matrices. Let's have A be 1, 0, 1, 1, 1, 1, 1, 0, 0. And then we'll add that to B, which is 1, 0, 0, 0, 1, 1, 1, 1, 1. Our resulting matrix is going to be exactly the same size. It's again going to be a 3 by 3. And we'll start out with this first row, first column, and we're going to add that to the first row, first column in B. 1 plus 1 is then going to give me 1. Then I'm going to go over to the next column. So I'm going to go first row, second column, 0, plus first row, second column, 0, 0 plus 0 is 0. Go over to the third column, 1, plus third column in first row in B, 1 plus 0, that's going to give me 1. Then I'm going to move down to my second row. First row, second row, first column, 1, plus second row, first column, 0, that gives me a 1. Move over, next column, 1 plus 1 is 1. 1 plus 1 again is 1. 1 plus 1 again for that third row, first column, 1. Third row, second column, 0 plus 1 is 1. Third row, third column, 0 plus 1 is 1. And that's the result of our matrix addition. So what we're going to see now is that the union of graphs and matrix addition are two parallel processes again, much like taking graph powers and matrix multiplication. So we have two principles that we're going to work with here. One, we've got that 1 in an adjacency matrix means that a directed edge exists in the graph. And a 0 means that it does not. And then we have an edge is in the union of directed graphs if it is in at least one of the individual directed graphs. Let's take a look at an example of how we can connect unioning graphs with the addition of graphs. Let's see how we can equate the unioning of graphs with matrix addition. Looking at this example, let's say we have the graph G and we have the graph H, and we'll have the matrix A and the matrix B associated with each one of them respectively. One thing to notice here is that if G and H don't have the same number of vertices, we're not actually going to be able to do matrix addition. Remember that the size of the matrix has to be the same in both cases. The dimensions have to be the same in order for us to be able to do the addition. And what that means from a graph perspective is that means that both G and H have to have the same number of vertices. Not necessarily the same number of edges, just the same number of vertices. Well, in this case, G and H both have 3 vertices, so we have compatible matrices. Now we go in, and if we were to go in and take the union of these two graphs, what we'd end up with is we'd end up with A to B. We'd have C to B. We'd have B to B, because those are all in G. Then, in addition to that, we'd have A going into A, because that's included in H. We'll notice that A to B, this directed edge here, is already in G. We've already included it inside of the union. We don't need to do that twice. And then we have C to A. That's going to be the last graph. Or excuse me, the last directed edge inside of the graph. So now our new edge set is going to have A to B, B to B, C to B, and C to A. And that includes all the directed edges that are included in both G and H. Now, if I go in and I do the addition, what we can see is we're going to get 1, 1, 0, 0, 1, 0, 1, 1, 0. Notice everywhere we have a 1 in A is going to be included in our A plus B. And in addition to that, everywhere where we have a 1 in B that's not also in A already, we're going to add in that 1 as well. And what you can see here, there's your AA, there's your AB, there's your BB, there's your CB, and there's your CA. And what we can see is that that directed edge set equates to the adjacency matrix in A plus B. That's pretty handy considering the fact that it's so much easier to go in and do the Boolean operations, the addition of the matrices, than it is to go out and draw the graphs. We're going to see in just a second when we create the transitive closure that this is going to be a much easier process for creating and constructing that transitive closure. To see how unioning two sets together and matrix addition utilizing Boolean algebras relate, what we should do is we should just take a brief example. And so let's say, for example, we have G here and we have H, and this is the matrix corresponding to J, and this is the matrix corresponding to H, and we have G union H. Now, if we have an edge inside of one of the sets, for example, in this case, if we have AB, we only need AB to be in one of the sets to have it be in the union. That's how the sets work. And so consequently, we take 1, and even though there is another 1 in H, those two, 1 plus 1, is just going to be equal to 1. So what that's saying is that the set's in G, the set is also in H, so the set will be in the union. Now, if we take a look, say, for example, we look at AA, well, AA is only in H. But remember, inside of a union, we only need for that edge to actually be in one of the sets. And so since it's in H, we end up with a 1 there. Now, also, 1 plus 0 in Boolean addition ends up equaling to 1. We only need 1, 1 in order to actually end up with a 1 whenever we do the addition, so those two actually correspond. Now, on the other hand, if, say, for example, I have AC inside of one of these sets, and I don't have an AC inside of the other set, so AC is not inside of either one of the sets, then what happens is I get 0 plus 0. That gives me 0, and that indicates for me that I don't have that particular edge inside of either one of the sets. All right. So again, if I go down here to the second row and I start out with BA, I notice that BA is not inside of either one of the sets. 0 plus 0, that's 0. BB is inside of set G, not inside of set H, but 1 plus 0 is a 1, and that means also that BB is inside of the union. We do that for each one of them, and what you can see, whether or not you go through and you actually union the sets or you utilize Boolean algebra, will end up with the same sets. Either we have G union set H, the edge set, or we have this matrix which corresponds to the addition of the G matrix and the H matrix. So now we have this idea of the transitive closure, which we talked about a bit more in depth in a previous video. And just recall that the transitive closure of a graph G is going to be the union of all the powers of G. So, like say for example, we've got G, G squared, and G cubed, right? And we could theoretically go up to G to the 4th, G to the 5th, all the way up to G to the infinity. But if you remember that if G has n vertices, we're only going to need to calculate up to G to the n to calculate the transitive closure. So basically all of the different kinds of walks and edges that we could create using walks of any length will be represented utilizing just the n different graphs that we have. So for example, let's say we have G, G squared, and G cubed in this case. So we go out and we calculate G squared from G utilizing matrix multiplication. So if you recall, if we multiply G, or A in this case, by itself, we get A squared. And if we multiply it by A again, we're going to end up getting A cubed. And so that's what these three matrices are. And they'll give us each one of these graphs. We have the walks of length 1, walks of length 2, and walks of length 3 for each one of those graphs. Now all we've got to do in order to calculate the transitive closure is we're just going to go in and we're going to add together these three matrices that represent G, G squared, and G cubed. And it's pretty simple. Anywhere where we have a 1 in any one of the 3 matrices, we're going to get a 1 in the resulting matrix because that's how Boolean addition works. So we notice that in both a squared and a cubed, we have 1s. And so we're going to get along the first row. So we're going to get 1s along the first row in the addition of the 3 of them. We'll get all 1s inside a squared and an a cubed for the second row as well. And then if you notice, we're going to have a 1 in that first column for the third row and 1s inside of the second and third columns for the third row. So we're going to get 1, 1, and 1. If you go in and you, in fact, union together all of these edges, what you'll see is that we'll have a complete digraph. That is, that we'll get every possible edge that we can get from the 3 vertices A, B, and C utilizing the graph G, G squared, and G cubed. So the union of these 3 is represented by this adjacency matrix and is calculated by adding together the matrix powers A squared, and A cubed. So essentially that's what we're going to do in order to find a transitive closure. All we've got to do is we've got to go out and calculate the matrices for A through A to the K and then add them all together. This is a lot faster than actually drawing these digraphs or even going through and unioning all of their edges, because we can utilize technology in order to go through and do this. It's very simple. And also the Boolean operations are also really easy to calculate as well. Let's take a quick moment to recap. So the union of graphs can be calculated and represented by adding adjacency matrices from the graphs. So that allows us to equate Boolean addition with taking the union of graphs. However, what we have to remember is to utilize matrix addition to add graphs, the graphs have to be the same number of vertices. If they don't have the same number of vertices, we end up with matrices that have different sizes. You can't add matrices that are of different sizes or have different dimensions. And so, again, same number of vertices inside of the graph. Now, in order to find the transitive closure of a graph G, what we want to do is, if G has n vertices and A is the matrix for G, we're going to find all the matrix powers from A all the way up to A to the n. We only need as many matrix powers as we have number of vertices. Then we'll add up all of the matrix powers from A to the n, and the resulting matrix then is going to represent the transitive closure for G. Because what we've done is we've taken all their powers and we've gone through and we unioned all those powers together utilizing matrix multiplication and matrix addition. Hi, I hope you've enjoyed working with graph powers and unions and finding the transitive closure and learning all about these things about how matrices relate to graphs. If you have, go ahead and click on the like button. If you have any questions, you want to comment, go ahead and send me a comment. And if you like the work that I'm doing, you want to learn more about discrete structures, discrete math, linear algebra, differential equations, calculus, anything along those lines, and continue this math journey with me, go ahead and subscribe to the channel.